Hello to everyone. Today I'll be discussing the pure rotational Raman spectra. In the previous class, we have discussed about the molecular structures, linear, triatomic, symmetric top, and you will see that the asymmetric top and spherical symmetries, or how these molecules are Raman inactive. So, as I discussed in the previous class, that the linear diatomic molecules and the top symmetric molecules having the same kind of ellipsoid, polarity ellipsoid. So now first I'll be discussing that the pure rotational spectra for the linear molecule. For the linear molecule, so if you remember that the energy of the rotational energy labels, this F of Z is equal to B of J plus 1 of minus D of Z square of J plus of 1. It's a cube. Centimeter inverse, where this J is equal to 0, 1, 2, and so on. So in a Raman spectroscopy, the precision of the measurement does not normally justify to retain this term. So that is centrifugal distortion constant. So we are not taking this part, then I have a simpler expression. This energy Fz is equal to Bjj plus 1 of centimeter inverse, where this J is equal to 0, 1, 2, 3, and so on. And these are representing my energy level. Now, the formal selection rules for this Raman spectroscopy delta Z is equal to 0 plus minus of 2 only. Now, if you look at it is contrasted corresponding to the selection rules for delta Z is equal to in a microwave rotational spectroscopy. This delta Z is equal to plus minus 1. The fact is that why these formal selection rules are corresponding to delta Z is equal to plus minus 2 only, or the 0 in the Raman spectroscopy. The reason is that the rotational quantum number changes by 2 units rather than 1 is connected with the symmetry of the polarity ellipse. For a linear molecule, such as we have discussed in previous class, that during the end over end rotation, the ellipsoid represents the same appearance to the observer twice. Means in the one rotation is one complete rotation, end to end rotation. Then you have a two axis of the two time it is showing that the polarity list in the same fashion. And however, it is equally clear that once you have a rotation about the bond axis produces the no change in the polarity around the bond axis, and end over end, that is the across the bond axis. So in the infrared and the microwave spectroscopy, we need concern ourselves only the end over the end rotations. So usual practice is that this delta Z is equal to this Z prime of this Z double prime, where this Z prime is a higher energy quantum number and Z double prime is a lower quantum number. So for the pure rotational changes, the upper quantum number must. So now here this delta Z is equal to minus 2, where I am ignoring or avoiding. The reason is that for the transition there must be always the higher quantum number must be the it is always necessary that the quantum number must necessary to be bigger than that the lower state. So, and this delta Z is equal to 0 is a trivial job, because the reason is that corresponding to delta Z is equal to 0, it means that you have simply the Rayleigh lines. Now combining that the delta Z is equal to, now this delta Z is equal to plus 2. Now then f of Z prime minus f of Z double prime is equal to simply this B of, it means that this J prime is equal to J double prime plus of 2. Then simply putting in this relation that B J double prime plus of 2 and J double prime plus of 3 minus B of J double prime plus of 1. Then you have simply this B z double prime square plus 2 of z double prime plus 3z double prime plus of 6 minus z double prime square minus of z double prime. From here simply you have this b and this cancels out. Then this is 4 of z double prime plus of 6, and simply I am written this double prime, I am removing that is for the convenience, this 4z plus of 6, where z is representing my lower n rotational quantum number, that is z double prime, lower quantum number. So if you remember, this corresponding to z is equal to plus 2, we have a S branch in a rotational. What I have suggested to you to just to go through this rotational spectroscopy and check that this selection rules. Then if you remember that delta z is equal to minus 2, minus 1, 0, plus 1 and plus 2. This is my O branch, sorry, this is Q branch. Plus 1, this is my R branch. And corresponding to minus 1 we have a P branch, minus 2 we have O branch, and plus 2 we have a S branch. So these are the branches of the rotational spectroscopy, rotational quantum numbers. Now simply I got this energy, this is delta, or this delta of F of Z is equal to, and we got this B of 4Z plus 1 of plus of 6, where Z is equal to 0, 1, 2, 3 and so on. So if the molecule gains rotational energy from the photon during the collision, that is in the Raman spectroscopy, we have a series of the S lines to the low wave number side to the exciting line. Means in a S branch, if these rotational energy levels gains the energy from my incident light, then they are providing you the Stokes line, lower wave number side. However, if these photons, these rotational energy levels of the S branch giving to the energy to the photon, then the energy is adding up, then we are getting the spectra in the positive side, that is the anti-Stokes line. So simply then I could say that simply this nu, that is the rotational of Raman energy in terms of the wave number, is equal to nu exciting plus minus of delta of this delta of Fz, then I could represent this delta of nu rotational, this delta of nu rotational is equal to nu prime plus minus of 4z b of 4z plus of 6 centimeter inverse. Now we got the energy of the output photons having the scattering one, that is the Rayleigh scattered, unscattered, excitation one, and is plus minus for this one. So if it is gaining the energy, then you have a negative sign. If it is giving the energy to the rotational states, then if the rotational energy levels are giving the energy to the scattered photon, then you have an anti-Stokes line. So now the transitions, if I will plot the transitions for this rotational linear molecule, so simply I have, this is 0, this is 1, 2, 3, 4, 5. So then you have 2 to 0, 3 to corresponding to this plus 1. Then you have this 0 to 2, 1 to 3, 2 to 4, 3 to 5. So these are these transitions we can represent the S branch if these S branch states are either gaining the energy from the photon or losing the energy to the photon. So each transition according to the Z value of the relative intensities of the linear. So now if I will plot these energies of these lines. This is my new excitation, that is a new prime what we have considered this new prime excitation one. If you look at the first line, this 4j plus of 6, I will be putting this j is equal to 0, then you have the 6. So 6 of b, the first line it is appearing at somewhere here, 6b, and you have a minus 6b. So this is 0, 0. Then you have another j is equal to 1, j is equal to 1, then you have 10. But the difference between that, the energy levels, then you will see that you have 6, then 4, so these are the energy levels. So 0, minus 1, minus 2, minus 3, minus 4, minus 6, and so on. And z is equal to 1, 2, 3, 4. It's a minus side. 1, 2, 3, 4, 5, and so on. So the first line, this is coming this 6 of B, and this is 6 of B. Then this is my 4 of B, and this is my 4 of B. 4 of B. In a pure rotational energy, so microwave, we have the difference between two rotational energy. That is transition delta Z is equal to plus minus 1. Then corresponding to energy difference between two subsequent rotational states is 2B only. Now here is 4B. The reason is that rotational symmetry of that polarity ellipse. So now the intensity, if you remember this variation of the intensity, why this intensity I am putting in this fashion, that if you remember that for a room temperature, we have energy distribution, this rotational J corresponding to this J value, we have this spectra. That is why we have this kind of the energy levels. So these are my transitions. So in particular, that the Stokes and the intensity line have the comparatively the intensity become mainly rotational level are populated, and hence downward transitions are the approximately the same as to the upward transitions. So if you remember that corresponding to the J, I have this kT divided by 2 of Hc of minus 1 upon 2 of something like that. HCB. HC of B. If you remember, corresponding to value of J, the most populated states are this one. So, if J is equal to 0, 1, 2, 3, 4, and 5, if I will plot that for a room temperature, then the population is in this fashion. So that is why, in the same fashion, I am putting that the intensities of these rotational lines in this fashion. Now, if you look at this upward and the downward transitions. Upward and the downward transitions are having the almost the same intensity. The reason is that according to this rule, this intensity of these rotational lines, they are well populated. These states are having the well population of the various energy as indicating the same intensities. Okay. So this is the pure rotational energies for my linear diatomic molecule. So once I am putting that the J is equal to 0, then this first line is appearing at the 6B distance. However, afterwards you have a difference between the two energy levels are 4B only. For a diatomic light triatomic molecules, the rotational Raman spectra will normally be the resolved now in a light triatomic molecules or the linear diatomic molecules, we have these lines are well resolved, and we can find out this constant B very easily. And if we recall that homonuclear O2 H2, if you remember, these homonuclear molecules doesn't provide you the pure rotational Raman, this microwave spectroscopy or infrared spectroscopy. However, these are providing you the Raman spectroscopy. So, the Raman spectroscopy is providing you that the technique which providing you the structural information of the molecules, as in this these diatomic molecules, the homonuclear diatomic molecules, the polarity is changing, and that is the if the polarity is changing, then you have the Raman spectra. And this technique is complementary to the microwave and the infrared studies, but merely the confirmatory techniques against the infrared and the microwave spectroscopy. Now, this is my pure diatomic molecule, this pure Raman spectra for the diatomic molecules, or the linear diatomic molecules, or the linear polyatomic molecules. So, if you have the heavier molecules, then in that case, it is very difficult to resolve these lines. And from here, it is difficult to find out this constant K. But however, along with the microwave and the infrared spectroscopy, it is always helpful to find out the structure of the molecules with the help of the Raman spectroscopy. Now, another example, another type of the molecules, that is the symmetric top molecules. Symmetric top molecules. Symmetric top molecules, if you remember in the last class, we have discussed that this for the CSCl3, if you have a top symmetric axis, if the top symmetric axis, if it's around, this molecule is rotating, then there is no change in its polarity. You have a circular cross section you are appearing. On the other hand, once you have an end to end across the axis, across the top symmetric axis, then you have an ellipsoid, and there is change in the polarity. So now the polarity ellipse for a typical symmetric top molecules, that is CSCl3 for example, NS3 is another example. So the plainly rotation about the top axis across produces no change in the polarity. By the end-to-end rotation will produce the change. So now this delta Z, so in the case of this top symmetric molecules, this delta F of K of Z, there are two quantum numbers, where this B of J plus of 1 plus A minus of B and K square centimeter inverse, where this Z is equal to 0, 1, 2, 3 and so on, and K is equal to plus minus of J plus minus of J minus 1 and so on. This K is the rotational quantum number, or this axial number of axial rotation. So if you have the symmetric top molecules, you have an additional quantum number K. This additional quantum number K provides you the axial rotation quantum numbers. So we'll see that what this K is playing a crucial role over here as a symmetric top molecules. Now this K square is sitting over here. So the selection rules for the quantum, this Raman spectra, we have delta K is equal to 0 and delta Z is equal to 0, plus minus 1, plus minus 2. These are except for K is equal to 0 states, where when delta Z is equal to plus minus 2 only. So except K is equal to 0 when delta J is equal to plus minus 2 only. So K is your rotational quantum number for axial rotation. So the selection rule delta K is equal to 0 implies that the change in the angular momentum of the top axis will not give rise to the Raman spectra, that is the Raman inactive. The restriction delta K, delta J is equal to delta J to plus minus 2 for K is equal to 0. You have delta Z is equal to 0 plus minus of 2 for K equal to 0. This is except for K is equal to 0 states when delta Z is equal to plus minus 2 only. So effectively delta Z cannot be plus minus 1 transitions. So for what will happen for delta, for in this case, now this delta Z cannot be plus minus 1. transitions involving the ground state j is equal to 0, and since k is equal to plus minus of j and plus minus to j minus 1 and so on. So delta k is equal to 0 implies that the changes in the angular momentum about the top axis will not give rise to the Raman spectra. Such rotations are the Raman inactive. The restrictions of delta z to plus minus 2 for k is equal to 0. K is equal to 0, delta z is equal to plus minus 2. Effectively, that delta z cannot be plus minus 1. For the transitions involved to the ground state, z is equal to 0 since k is equal to plus minus of j. So thus for j values other than 0, k also may be different from the. So what will happen that, now this is very crucial. So j values other than 0, k also, if j is not equal to 0, k may also different values at delta z is equal to plus minus 1 transitions are allowed. If j is equal to not 0 but delta z is equal to plus minus of 1 is allowed transitions. So I have three cases. We have three cases. Now number one, this delta z is equal to plus of 1, that if you remember, that is the R branch. So this delta of f of R z is equal to this f of z prime minus of f of z double prime, and is simply this f of b z prime plus of 1 and minus b z double prime of z double prime plus of 1. So simply we have this plus 1, it means that this z prime is equal to z double prime plus of 1. And simply once you will be solving that, you will be getting this 2b of z plus 1 of centimeter inverse. But the case is that, but z cannot be 0, means z is equal to, you have this j is representing lower energy states, this 1, 2, 3 and so on. This is the condition. So another is delta z is equal to 2, delta z is equal to plus 2. Corresponding to delta z is equal to plus 2, what we have? This delta z is equal to plus of 2, that is the S branch, delta of f, that is S branch, this j is equal to simply this f of this j prime minus f of j double prime. Now here this j prime is equal to j double prime plus of 2. What we did in our pure linear diatomic molecule or the linear molecules. So simply I will be getting that this b of 4j plus of 6 centimeter inverse, where this j is equal to 0, 1, 2 and so on. Now the selection rules, this delta j is equal to plus 2 when this j is equal to 0, 1. These are the quantum numbers for the lower energy states. In the previous case, this dependency of that k, that is a rotational symmetry, then you have, if delta j is equal to plus 1, in that case j lower energy cannot be my 0. So if I will be combining all these relations, that this, now we have an R branch and S branch, So nu of R branch of Raman is equal to nu excitation plus of minus delta of fj, that is equal to nu prime excitational plus of minus, that is excitation plus of 2bj plus of 1 centimeter inverse, j is equal to 1, 2 and 3, and this nu S branch Raman is equal to nu prime plus minus of b of 4j plus of 6 centimeter inverse where j is equal to 0, 1, 2 and so on. Where this j is a lower in quantum numbers. So once I will plot it, once I will this energy diagrams corresponding to this, so what I will get at this distribution of this, as we know that the most probability states that the intensity from their result. Now the first is R branch. So you have new excitation. So the first line, if you remember, that is for this new R line of Raman is equal to, you have a new excitation plus minus of 2bj plus of 1. If j is equal to 0, then you have the first line is coming at the 2b distance only. This is 2b, j is equal to, sorry, j cannot be my 0. So what I could put, that is the j is equal to 1, then you have this 2, then the 4. So the first line it is coming corresponding to this j is equal to 1, then you have this line, then this 1. So in other side, the same fashion that j is equal to 1, 2, 3, 4 and so on, this 1, 2, 3, 4 and so on. So the first line it is coming at the 4b. Afterwards, the j is equal to 2, then you have 6. Then you have 4b and 6b, and then this difference is 2b only. 2b only. So you have this line, this line, this line, this. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. S branch. For the for the R branch, for the P branch, S branch, this new prime. But you have new S branch of Raman is equal to new plus minus of this 4b plus of 6. For j plus of 6b. If j is equal to 0, then you have the 6b. So first line is coming at your 6b, that is the 0. And this is 0, that is the 6b. 6b and 6b. Another line, that is the j is equal to 1, then you have a 10 of b. So 10 of b. So 2 corresponding to this 2, then 3, 4, 5. Now in this case, the separation is just double. So you just, this is 4b corresponding to this 1, you have this, then the difference is almost double as compared to the upper lines. If just a double of this one, so you have this, then this, then this, and this. So the same fashion in the left hand side as well. These are the S lines where the difference between these energy levels is 4b. The first line is appearing at the 6b, here is a 4b. The difference between this 2b and then this is a 4b. Now, if I will combine these two lines, what will happen that corresponding to the 0, you have a 0 line and the 1. So, what will happen if you will just add to them? So what I will get the complete spectra. Now this 1 correspond, this is 1, this is 0, that is 4b. This 1 is appearing over here. So if I am saying 0, 1, 2, 3, 4 and so on, now I am representing this, suppose this S line, S line, S line, S line, S line, S line, and this is the S, 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 S and S and S. So at a 4b, the first line is R line, that is at 2b distance, that's a 4b distance, this is a 6b distance. At the 2b distance, I will be getting this one. This is R. Now this R, then this, then the second line corresponding to the 0 at the 4b distance. This is the 6b distance. Now this is 4b. Now this is at the 6b distance. This is at the 6b distance. What will happen? This intensity will be added off. So what I will get now, the complete spectra, what I will get? This one. These are the lines. What will happen that these are adding, the intensities are adding, and the alternate of lines are the smaller one, and the or this alternate line are the intensity having the S branch as well are the R branch. So in R branch you have a difference between this 2B. In an S branch you have a 4B. Now the combined, once I am combining the S branch and this R branch in a complete spectrum, the intensity lines will, alternate lines will be the intensity will be the higher as compared to the other will be the less. So this is a complete asymmetric top molecules, and the alternate R lines is overlapped by the S lines. Alternate lines of the R branch will be overlapped with the S branch. Then you have the intensities are in this fashion. In the same way in the your this Stokes line as well. And it should be noted that it is not; these are not connected to the nuclear spins. So nuclear spins we have not discussed about how this nuclear spins also influence our Raman spectra, and that depending on the spin, either it's the zero spin or the half spin or the one spin, then also it influences this. So that is why we can find out the spin of the nucleus also diagnosed or the characterized with the health of the Raman spectra. So now another type of the molecules what we have, I was discussing that a spherical top molecules or asymmetric top molecules. So spherical top molecules, the tetrahedral symmetry of the CS4 or this that is SiS4, the polarity ellipse for such molecules is spherical surface, and so it is evidence that once there is a rotation of the ellipsoid will produce no change in the polarity. So therefore the pure rotations of the spherical top molecules are completely the inactive of the Raman. So the normally all rotations of the symmetric top molecules on the other end are the Raman active. So if the top symmetric molecules Raman active, top asymmetric molecules or the spherically symmetric molecules are not changing their polarity on its rotation. So these molecules are the Raman inactive molecules. So now in the tomorrow lecture I will be discussing the vibrational Raman spectra and the Raman activity of the vibrations. We'll see that how this is are the crucial. So just to go through this one and this little bit about this linear molecules, symmetric top molecules, and diatomic molecules. Once you are finding out their angular momentum or this moment of the inertia about its axis, across the axis, you need to check that when is the polarity changing and when it is not. So for the today lecture, so I'll be stopping here. Then tomorrow I'll be discussing that the Raman activity of the vibration. This is so important. Thank you.